Okay, so welcome back to mathematics class, and we were talking about circles. So let us see how far we have covered. Till now we have covered till circle through 3 points, right? In the last class this was the last topic. Now in this class we will look at equal chords and their distances from the center, angles subtended by an arc of a circle, and finally we will look at cyclic quadrilaterals. So let us start off with topic number 5, which is equal chords and their distances from the center. So let us look at what is the distance of a line from a point. How do we define that? To show it, we draw different lines from the point to the line. You can see we have drawn different lines which join the point and any other point on the line. And you can see from the figure that the shortest line between the point and our line AB is the perpendicular line PM, right? PM is the perpendicular line, and you can see it is also the shortest line between the point and the line AB. So we can define the distance between a point and the line in this way. The length of the perpendicular from a point to a line is the distance of the line from that point. The length of the perpendicular from a point to a line is the distance of the line from that point, right? And we will use this to define what is the distance of a chord from the center of a circle. And it is the same thing as well. The length of the perpendicular from the center to the chord is the distance of the chord from the center, right? This perpendicular line segment, which is OM, is the distance of this chord AB from the center O, right? So now we look at a theorem, and the theorem states equal chords of a circle or of congruent circles or similar circles, equal chords of a circle are equidistant from the center, or we can say equal chords are spaced equally apart from the center, right? Here from this figure we can see, if we consider PQ and RS as the equal chords, then their distances from the center, which is OL and OM, must be equal. This is what the theorem states. Now how can we show this? So for this we again do some simple constructions, right? We join OQ and OS, as you can see. Now let us consider these two triangles formed by it, triangle OQL, this one, and triangle OSM, this one. So let us consider these two triangles. Now here you can see OQ equals OS, right? Because their lengths are equal to the radius of the circle, right? Because O and S is the fixed distance from the center, which is the radius. So we get OQ equals OS. Then we get LQ equals MS. And why is that so? Because from the earlier classes we have got that the chord is bisected by the line joining the center, which is perpendicular to the chord, right? If a line is drawn to the chord which is perpendicular to the chord, it bisects the chord, right? Here OL is drawn perpendicular to the chord PQ, so it bisects PQ, right? Or PL is equal to LQ, and this SM is equal to RM, right? These are equal chords, so as they are bisected, their individual parts must be equal to all of them, right? As PQ equals SR, half of PQ must also be equal to half of SR. So LQ must be equal to MS, right? From the earlier theorems we had learned in our classes. So next we get angle OLQ, which is this right angle, is equal to angle OMS, which is this right angle, and they are also equal, right? Both of them are right angles. So again we get three criteria to show that these two triangles are exactly alike. So we get triangle OQL is congruent to triangle OSM, right? We get these two triangles are congruent to each other by the RHS rule. We have a right angle, a hypotenuse, and a side, right? Here also right angle, hypotenuse, and a side. So by this principle we have proved that these two triangles are congruent to each other. Now by CPCT we can easily say that OL must be equal to OM, right? Because as they are congruent to each other, they can exactly overlap onto each other, and therefore their corresponding parts must also be equal. So OL is equal to OM, and therefore we have proved that equal chords of a circle PQ and RS are equidistant from the centers, right? The equal distances from the center are OL and OM, right? These two distances from the center are equal. And you can also state this theorem in the other way around, which is the converse of this, which is chords equidistant from the center of a circle are equal in length. Or if we draw two chords at equal distances from the center, then the two chords will have the same length, right? In the given theorem we knew that the chords were of equal length, and we were finding the what is the relation between the distances from the centers, and in the converse we know that the distances from the centers is actually the same, and we are comparing the lengths of the chord, right? So anyway we can say that if the chords are equal, then the perpendicular distance from the center is also equal, right? So let us solve a question using this principle. If two equal chords of a circle intersect within the circle as shown, prove that the line joining the point of intersection to the center makes equal angles with the chords. Or if two chords, we have considered AB and CD, if these two chords are intersecting at point M, then the line joining this point M with O makes equal angles with the chords. We have to prove this. We have to prove that these two angles are actually equal to each other. So let us see how can we prove this using the theorem we have just learnt. So what we do, we draw simple constructions, which is OI and OJ. OI is perpendicular to AB, OJ is perpendicular to CD, right? We have made these constructions. Now consider the two smaller triangles OIM and OJM. Let us consider these two triangles so that we can include these angles in our calculations. So from the figure we can say OI equals to OJ. And how can we say this? We have learned just now that if two chords are equal, then the perpendicular distance from the center is also equal for them, right? And here it is given that two chords AB and CD are equal, so their perpendicular distances from the center must also be equal, right? So from here we get OI is equal to OJ, and don't forget to mention the reason by the side. So the second part which we get, IM is equal to IJ, IM is equal to JM, or rather we can say this, that as the chord is getting bisected, at this point, right, this point of intersection, we can say that it is the point CM, the line segment CM and MB is equal. So if we subtract this length from the half of this chord, we can easily say IM equals JM, right? These two sides we have got as equal as well. Or you can also find it out with the angles, it doesn't matter. And we get OM common to each of them, right? OM is common to each. So you can see we have got three criteria which prove that these two triangles are congruent to each other. So we write that explicitly. Triangle OIM is congruent to triangle OJM. Also alternatively, you could have used this is equal to this, OM is common, and also you could have used these angles. These two angles are equal, and also you could have said that these two triangles are congruent to each other, right? By this rule, which is right angle hypotenuse side, RHS, by this rule also you could have said triangle OIM is congruent to triangle OJM, right? So anyway, we have proved that these two triangles are congruent to each other. So now the corresponding angles, which are IMO, this angle, and this angle, angle JMO, are equal, right, by CPCT, corresponding parts of congruent triangles. So you can see we have proved that the angles which is made by the line joining OM are equal, right? The line joining OM makes equal angle with the chords. This angle made by the chord is equal to this angle. So finally we get what is required in the question, that the line joining the point of intersection to the center makes equal angles with the chord. So what have we done? Let us recap once again. We have considered two triangles. First we had constructed two perpendicular lines on the chords, and we have used the concept that these two perpendiculars have equal lengths as the chords were equal. Then we have shown that the smaller triangles which has been constructed are congruent to each other. From there we have found out that the corresponding angles, which are the adjacent angles rather, IMO and JMO, these two angles are the same, right? And this proves the given question. So let us jump into the next topic, angle subtended by an arc of a circle. And what is it? If we consider an arc PQ, which is the part of a circle, if we consider an arc and join the two points with the center, and the angle made by those two lines is actually the angle subtended by the arc at the center. This is the angle subtended by the arc PQ at the center, right? And if you draw similar arcs of equal lengths, you will find that congruent arcs or equal arcs of a circle subtend equal angles at the center. And why is that so? Because In our earlier class we had seen equal chords subtend equal angles at the center, right? But what if we did not consider that chord and we considered only the arc made by those same endpoints, right? If we considered the arc made by those same points and we had neglected the chord, even then the angles subtended would be equal, right? So you can imagine an invisible chord joining PQ, and if you are drawing two equal arcs, that means you have two equal chords which are joining the endpoints of the arc, and as these two equal chords subtend equal angles at the center, similarly equal arcs also subtend equal angles at the center, right? Now here comes an important theorem. The angle subtended by an arc at the center is double the angle subtended by it on any other remaining part of the circle. For example, in the first figure, if we consider the minor arc AB, the smaller arc AB, the angle subtended by it at the center is AOB, right? This is the angle subtended by it at the center. But if we consider the angle subtended by it at any other part of the circle, for example, let us consider the angle subtended at P, which is angle APB. APB is the angle subtended by the arc AB at P. So according to the theorem, this angle, which is subtended at the part of a circle, is half of this central angle, or the central angle which is subtended by the arc is double that of the angle subtended at any other point on the circle, right? And mind it, both of them, the angles should be on the same side of the vertex. Like for this angle P was on this side, right? Angle P was below the vertex P, so angle O must be below the vertex O. You must consider the same angles. And in the second figure, this angle AOB must be double that of angle APB. This is what is stated by this theorem. The central angle subtended by the arc is double that of the subtended angle by the same arc at any other point on the circle. And for the last one, if this is the angle subtended by the major arc AB, if this is the angle subtended by the major arc AB, then this angle APB is half of angle AOB, right? And you can see we are considering angles on the same side, right? So we have seen that these angles, the central angle is double of the angles made at any other point on the circle. Now how can we prove this theorem? Let us take any random example. Like here we have taken, for example, the first one, angle BOA, we have taken the central angle subtended by the arc AB, and we have taken point C on the circumference of the circle, and the angle subtended by the minor arc AB is taken here as angle ACB, right? And we need to prove that this angle is double of this smaller angle, right? We need to prove this. So how can we prove this? So let us start by simple constructions once again. So we join CO and extend it to M. COM is a straight line and M lies on the circumference of the circle, right? We have drawn a straight line joining CO and M, right? Now let us label the angles formed by the straight lines and the radius of the circles and the chords, of course. So we have labeled the angles as x and y. You can see we have labeled this angle and this angle both as x. And why is that? If you see triangle BOC, this arm is nothing but the radius of the circle. This arm is also the radius of the circle, right? So triangle BOC is an isosceles triangle with BO equals CO, right? So BOC is an isosceles triangle, so their base angles, which are this angle and this angle, must be equal, right? And also for triangle AOC, if we see OC is the radius as well as OA is the radius, so both of them are equal. So again their base angles, which are this and this, must also be equal, right? Because it is an isosceles triangle. And we have named them X, X and Y respectively. You can see we have named the angles on the left hand side, which is of triangle BOC, we named them as X, and of triangle AOC we have named the equal angles as Y, right? So let us see how we can find out how we can prove the given theorem. Now if we consider the exterior angles, let us consider this angle first. This angle is the exterior angle of triangle BOC, right? This is the exterior angle of triangle BOC. And what is the measure of this angle? Exterior angle is nothing but the sum of the interior opposite angles, right? Or the sum of X and X will give us the exterior angles, right? The interior opposite angles. So we get the exterior angle, this one, angle BOM, as 2x, right? Angle BOM we get as 2x. Similarly, as this line, the line we had drawn, is exterior to triangle AOC also, this angle, this exterior angle will be the sum of interior opposite angles, this one and this one. So this exterior angles comes out to be 2y, right? So we get here 2x and 2y. So let us add up these angles. So angle BCA, which is this angle at the circumference, is the sum of these individual angles, which is x plus y, right? This angle measures x plus y. And if you see this angle, the central angle, what is the measure of this? It is 2x plus 2y, right? 2x plus 2y, or we can take 2 common out from them, and it is 2 into x plus y, right? 2 into x plus y. So can you see the this angle is x plus y, but the central angle is twice of x plus y. Or we can say BCA, which is x plus y, is half of angle BOA, which is twice x plus y. Or this angle is half of the central angle. This angle is half of the central angle, right? So we have proved the theorem that angle subtended by an arc at the center is double the angle subtended by it at any other point of the circle, any other remaining part of the circle, and of course that remaining part must be on the opposite side of the angle subtended taken, right? Here you can see we have taken the point on the circumference at the opposite side of the subtended angle. So let us use this theorem to prove one more theorem, which is angles in the same segment of a circle are equal. Now here you can see a circle with two angles drawn Actually it looks like a bow, but they are two different angles, which are, if we consider AQB and angle APB, if we consider in this way, or we are looking at the major segment formed by AB line segment. If we look at the major segment, which is this part, if we look at this major segment, we see that we have two angles, AQB and APB. We have these two separate angles, right? If we consider angles on the same segment. Now we have to prove that these two angles are always equal. How can we use the theorem we have just learned to prove this theorem? Let us see. Let us do construction once again. We join AO and OB, right? We join center with the endpoints of the segment or the endpoints of the chord AB. Now we can easily use the theorem we have just learnt. Angle AQB, which is this angle, is half of the central angle AOB. And why is that? If we consider this arc AB, the minor arc, the angle subtended by this arc at the center is angle AOB, and the angle subtended by the same arc AB at Q is angle AQB, right? So this angle AQB must be half of angle AOB, right? The angle at Q must be half of the central angle. So we get the first equation. We again consider the two sets of angles, angle APB and angle AOB once again. And here, if we look at the minor arc AB once more, AOB is the central angle and APB is the angle made at the circumference at point P, right? So we can say this angle, angle APB, is half of angle AOB once again, right? This angle subtended at the circumference is half of the central angle. So now you can see both angle AQB and angle APB both equal to half of the central angle, or both of them must have the equal measure, right? Both of them must have the equal angle measure, right? So we have proved the given statement. Angles in the same segment of the circle are equal, and we can use this theorem also to solve different questions. This statement can also be taken as a theorem, and please remember, whenever you are using a theorem, don't forget to state the theorem after you have used it. So let us look at our last topic, which is the cyclic quadrilaterals. So what are they? A quadrilateral ABCD is called cyclic if all the four vertices of it lie on a circle. You can see we have a quadrilateral ABCD and all the four vertices are lying on a circle. All the four vertices are lying on a circle, right? All the four vertices are lying on a circle. So such kind of quadrilaterals are called as cyclic quadrilaterals because their vertices are lying on a circle. Now one of the special characteristics which we have for such kind of figures is that sum of either pair of opposite angles of a cyclic quadrilateral is 180 degrees. Or if we consider one pair of opposite angles, which is angle B and angle D, these two angles must add up to 180 degrees. These two angles must add up to 180 degrees. This is a special characteristic of cyclic quadrilaterals. And also if we consider the second pair of opposite angles, which are angle A and angle C, if we consider these two angles or this opposite pair of angles, angle A plus angle C must also add up to 180 degrees. So we get angle B plus angle D must add up to 180 degrees, right? And also we get angle A plus angle C, which are opposite angles, must equal 180 degrees, right? So this is a special characteristic of cyclic quadrilaterals, and this can be stated in a converse way also. If the sum of the opposite angles of a quadrilateral are 180 degrees, the quadrilateral is cyclic, right? If we have angle B plus angle D is 180 degrees and also angle A plus angle C is 180 degrees, then we can always consider that the quadrilateral is a cyclic quadrilateral, right? Now can you think of a cyclic quadrilateral which is a figure which we know, like whether square, rectangle, parallelogram, which of these are cyclic quadrilaterals? You will see that both square and rectangle are cyclic quadrilaterals. Why? As all of their angles are 90 degrees, obviously opposite pairs of angles must add up to 180 degrees, right? Opposite angles must add up to 180 degrees, and therefore both the rectangle and the square are special cases of cyclic quadrilaterals as well. So let us use the characteristics of cyclic quadrilaterals in a question. In the given figure, this is the figure, AB is the diameter of the circle. AB is the diameter, you can see it is passing through the center O. CD is a chord which is given here. CD is a chord which is equal to the radius of the circle. CD is equal to the radius of the circle. Now AC and BD, when extended, intersect at a point E, which is shown here outside the circle. When AC and BD are extended, they intersect at E. So we have to prove that angle AEB, which is this angle, we have to prove that this angle is 60 degrees. We have to prove that this angle is 60 degrees. So let us see how we can do it. So you can see, if we draw OC, OD and BC, BC we will consider it later, but still we have drawn it to do all the construction at once. So first let us consider OC and OD. You can see OC and OD are the radius of the circle and they are equal, and also CD is given as equal to the radius of the circle, or OC equals OD equals CD, right? Or the three sides of the triangle OCD are equal. Therefore we can say triangle OCD is equilateral, right? OC is equal to OD equal to CD, or we have got OCD is an equilateral triangle. So all of the angles must be 60 degrees, right? So all of the angles must be 60 degrees as all of the angles are equal. Therefore we consider one of the angles, angle COD. This angle must be 60 degrees, right? All the sides are equal, so OCD is an equilateral triangle. So any angle of an equilateral triangle is 60 degrees. Now angle CBD, which is this angle, angle CBD is half of angle COD. And why is that so? If you look it in an inverted fashion, now try to rotate your eyes 180 degrees and try to imagine this figure. If we consider the arc CD, if we consider the arc CD, The central angle subtended by it at O is angle COD, right? This is the central angle subtended by the arc CD. And you can also see the arc CD subtends an angle at B. The arc CD subtends an angle at B, which is at the circumference of the circle, right? And it is on the same segment, right? So this angle must be half of the central angle, right? This angle must be half of the central angle. So angle CBD is equal to half of angle COD, or the angle subtended by an arc at the circumference is half of the angle subtended by that arc at the center, right? This theorem we had learned just now. So we get angle CBD equals 30 degrees, right? If this angle is 60 degrees, the smaller angle must be 30 degrees, right? So we are getting the measure of angles one by one. Again, angle ACB is 90 degrees. And how? We use the same principle once again. If you see the arc AB, if we see this arc AB, the central angle is AOB, right? The central angle subtended by this arc is AOB, which is the diameter itself. And as the diameter is a straight line, this arc must subtend an angle 180 degrees at the center, right? The arc AB subtends an angle of 180 degrees at O. And also you can see this arc subtends an angle at C. This arc AB subtends an angle at C, which is at the circumference. Now, the angle subtended by the arc AB at the circumference is always half of the angle subtended by this arc at the center. So angle subtended by it at the center is 180 degrees. So angle subtended by the same arc on the circumference will be 90 degrees, right? So we get angle ACB is equal to 90 degrees, as ACB equals half of angle AOB, right? So we have used the same theorem twice. Now BCE, this angle is equal to 180 degrees minus ACB, right? 180 degrees minus ACB. Now ACB is 90 degrees, right? We have got ACB as 90 degrees. So BCE we can get easily as 180 degrees minus 90 degrees, which is 90 degrees only. So we get this angle also, this angle BCE as 90 degrees. So you can see in this triangle, triangle BCE, we know angle C, we know angle B. The only unknown is our required angle, angle E, right? We know these two angles. Angle BCE is 90 degrees and angle CBE is 30 degrees, right? So angle CEB or angle E is nothing but 180 degrees minus sum of the other two angles, and if we do this we get 60 degree as angle E, right? So angle CEB is nothing but the same as angle AEB. So we have finally got AEB as 60 degrees as required, right? So let us recap the step once again. First, we try to find the central angle subtended by the arc CD. We see that triangle OCD is equilateral triangle. Therefore, angle COD was 60 degrees, right? We had found initially that this was angle 60 degrees. Then we found out that if this is 60 degrees and is the central angle, then angle at the circumference by the same arc will be half of it, or this angle will be 30 degrees, right? This was 60 degrees, so angle B is 30 degrees. Now, to find one more angle of the triangle BCE, we see that angle ACB is 90 degrees because it is the angle subtended at the circumference by the arc AB. By this arc, the angle is subtended at the circumference at C, right? And as this angle subtended by the diameter is 180 degrees, this angle will be half of it because it is on the same arc. So 180 degrees divided by 2, we get this angle as 90 degrees. So by considering this is a straight line, ACE a straight line, we get the measure of this angle as 90 degree once again, right? We get the measure of this angle, angle BCE, as 90 degrees. Now for the triangle BCE, we know that this angle is 30 degrees, right? This angle is 30 degrees, this angle is 90 degrees, and only unknown is this angle, and we can apply the sum of all the angles of a triangle, which is 180 degrees, to find out angle AEB as 60 degrees, right? So you can see how we can use the same theorem again and again, or use different theorems to solve a question very easily and in less number of steps, right? So here we complete circles, and in this class we have learnt about the equal chords and their distances from the centers, which are also equal, right? Then angle subtended by an arc of a circle. Then finally we had learnt different characteristics, or one of the major characteristics of cyclic quadrilaterals, right? The sum of the opposite angles are 180 degrees. Thank you and see you again.